on the syllabus or about anything that I talked about last time. If you don't, that's fine. I know sometimes no one wants to be the first one to speak. So it's also really weird for me to start out a class, like seeing you for the first time, not on the first day. So like I'm about to jump into material here and I barely even know you, except for the half of you that look really familiar to me. Also, feel free to use the chat feature. I know not everybody has a working microphone, and that's okay. If you want to chat me, that's fine. Usually it beeps when there's a chat. Occasionally it doesn't, and I never can figure out why. It's bizarre, but lately it's been working. So if you send something in the chat and if someone notices there's something I haven't addressed, feel free to somehow tell me. There's also a raise hand feature that you can use. I think it's at the bottom of your menu, depending on what you're using to access the class. Sometimes students use it a lot during the summer, actually, and I found it really helpful because if you raise your hand and I'm like in mid-sentence, at least it gives me a second to finish my thought, and then I can address your question. Yeah, so it's just easier. Plus, a lot of times people feel weird just kind of butting in and saying like, I have a question, because it's not the same as being in class and like I can't see you as well. So there's that. If you keep your cameras on, that's really helpful to me. Like I said, in your intro video, which hopefully you watched, I didn't even see how many views it had. Sometimes I try to check to see what's going on, but I never know if there's some like overly worked student who's just watching it over and over again. So my view count isn't necessarily accurate. Switch. All right, well, I'm gonna have to do that later. Okay, someone had emailed me before class asking about the recordings for the lectures. I mean, there is, by the way, I mean, I said it in the video, but there is an attendance policy, but I will be recording all of the lectures. So there'll be a link available to you on YouTube, and I'll put that in D2L for you. It's not going to be available right away because it takes a while for me even to get the video at all. Like Gmail has to, or Google has to actually like finish processing it and everything, and then they email me, and then I have to upload it to YouTube. So it takes some time. However, if you accepted the calendar invite, which most of you did, sometimes every semester I have like several students who don't accept, and I don't know why. That's fine. Maybe they just don't want to get notifications, but you can turn them off. If you accept the calendar invite, then the Google Drive link will be in the calendar entry for that day. So whatever we do today, you can go back to your Google Calendar for today, and there'll be a Google Drive link to this. So you will have two options for how you want to watch the recorded lecture, whether it's on YouTube or whether it's on Google Drive. Okay. This says no views. That's not possible because when I checked it like 2 days ago, it had several views. It could be fuddled. Let's find out. Oh, 28 views. Perfect. Interesting. All right. Well, if there aren't any questions, I'll just start covering 6.1. I sometimes feel bad not having you all introduce yourselves, but it takes quite a bit of time. Maybe we should do like 3 people a day. Should we do that? Yes, let's do it. All right. And unfortunately, I'm going to start right at the beginning of the alphabet. Let me see who's here. Arib, you are the first one. Can you hear me?
Yeah, I can hear you.
Yourself.
I can hear you.
There you are. Tell us about yourself.
Well, my name is Arib, right? I really like math. I think math is my favorite subject. and I'm also really into sports and exercise. And yeah, I think that's about it.
Cool. What kind of sports?
So right now I play track and field. That's like my main sport, and then I've also been trying to get more into volleyball, but it's a bit tough because it's not as popular, at least on my level, for men at least. And so I'm trying to get into more clubs and stuff, and then hopefully work my way up. But that's where I'm at right now.
Okay, good. What do you plan to major in?
I'm kind of stuck between biochem and neuroscience. Like right now, I want to do just associate science, and then biochem is really interesting to me, just because like it has to do with your body, right? Like how everything is generated and destroyed. And I think as of right now, like we don't understand that as much as we could. So it'd be cool to learn more about that.
Yeah, definitely. That sounds awesome. Well, I'm glad to have you in class.
I'm glad to have you as the teacher.
Thank you.
And how do you pronounce it, Miss Faruqi?
Faruqi. Yeah.
Faruqi. Okay.
Yeah. Yes. Q, not a G. Even after I got married, I was like, why can't I log into my new email account? And they were like, we changed it for you. It's there. And I'm like, no, it won't let me in. And they were like, oh, let's come help you. And they acted like I didn't know what I was doing. And it turned out that they had set it up as kfarugi@elgin.edu. I'm just like, really? Terrible. My son's preschool stuff, it all says Oscar Farugi on it. Like,
Wait, so the correct one is with a Q or a G?
it's a Q.
Okay.
Yeah. I think it throws people off because there's no U. It's just Q. And then a lowercase q looks like a G.
Mm-hmm.
Yeah. But yes, Faruqi. Thank you for asking. Okay. So Zane, you're next. You know what? Zane might not have a microphone. Do you have a microphone, Zane?
I have a mic, yeah.
Awesome. Okay. Tell us about yourself.
So my name is Zane. I'm a sophomore, and I'm actually dual enrolled at ECC, so here, and UIC. So I'm going to UIC for most of my classes, but some of the side ones, like Calc 2, I'm taking here just for like convenience, so I don't have to commute all the way there on extra days. I'm a CS major, so calculus is pretty important for fulfilling my degree requirements.
Mm-hmm.
And yeah.
Were you born in Pakistan? Sorry, I'm going off our chat earlier.
Actually, no. I was born here, but my parents were born in Pakistan. They came, so yeah, both of them moved here, I think, shortly after they got married.
Mm-hmm.
But yeah, I was born here.
You were born here. Gotcha.
Mm-hmm.
My husband was born in India, but his family moved him here when he was 2. So
Oh, wow.
He's pretty much always been here. He has no memories of India. Okay. What else was I going to ask you? Oh, you pretty much told me everything. My niece just started at UIC in the graduate school for public health. She's very excited. Okay. The next person on the list is me for some reason. Becky, you are next.
Okie dokie. Well, I am happy to be in your Calc 2 class. Had you with Calc 1, which was great. I'm computer science major. Let's see. I have a golden doodle. She's a little over a 1. She's a terror. And sadly, I think I have 14 credits this semester, so it's going to be a little fun.
Well, hopefully it's not like chemistry, computer science, physics, and Calc 2.
I have computer science. I have a humanities class. I have another computer science class, and then your class.
Okay. All right. Well, hopefully it won't be too bad. And my class will be so fun that you won't even notice. I'm sorry. Go ahead.
I said I'm hoping not, but yeah.
All right. It's such a small class. Let's just have everyone introduce themselves today. I want to know everybody. Burfin, you're next.
Well, I'm Burfin, and this is my second time with Miss Faruqi, and I'm really excited for this class because I really enjoyed your class last semester, this summer actually.
I know, it wasn't that long ago.
Yeah, and I'm planning to transfer to ASU for aviation management and professional flight.
Oh,
So hopefully it will work out for me. But I have 18 credits this semester. So I'm really anxious, but hopefully it'll be okay. And I'm working too, so
mhm. All
but
right.
yeah.
This is making me nervous.
We'll
I
see how it
wonder if
goes.
ASU like Arizona State University? Why?
Because the weather is always so nice that like it's the perfect place for like flight students basically. Like you can fly every
Oh,
day.
I see.
And yeah, I've been there before for like just visiting. And I really like the campus too, so I was like, why not?
All right. Well, I don't think I knew that about you. I'm glad you told me just now. I stopped having students introduce themselves like 2 semesters ago because it took so long, and I was just like, no one's got their camera on anyway. But we're doing it today. Steven, I think I only have one Steven.
Hello.
Hello, there he is.
Uh, well, I like to play video games. I like gardening a lot. I've like started like buying a lot of plants just because I have nothing better to do. I actually have taken this class already. I took it in high school, but I like didn't do the AP exam because I'm like really, really bad at online school. Um, but I want to be an aerospace engineer. I think I don't really know what I want to be. May some like just in some way change to like computer science or something. I like am really inexperienced and don't know anything about engineering, so I'm kind of just like all over the place. But yeah, I'm kind of excited for this class again, just because I don't know, it'll be
Cool.
easier.
Yeah, I feel like so many students are like, I want to major in engineering, but I don't really know what it's about. I was like, I was an aerospace engineering major, and I was like, I don't really know. And then when I got into it, I was kind of like, I don't think this is what I wanted to do. Burfin, did you have a question?
I just want to add something to that.
go
I
ahead.
actually wanted to do aerospace engineering too, but
Really?
then I checked like their like curriculum, like all the classes I had to take, and then I was like, no, thank you. And then I like realized eventually like flight was much easier and like, you know, better option for me. So,
I see.
but
Yeah.
it's a really cool major, I think. Yeah.
Yeah, I think so too. I went to U of I for aerospace engineering actually, but it was at U of I in like my junior year where I was like, I don't think I want to do this anymore. And everyone was yelling at me. They were like, what are you doing? Like, you're going to regret this one day. I've actually never regretted it, just so you know. I
Yeah, that's
love what I'm
actually
doing
probably
now.
gonna be me too. I want to go to U of I. I like want to transfer next year and then do that. So I don't know, but I don't know. It'll be fun regardless, even if I end up switching. So
Yeah, well, it's nice to have the option. The good thing is when you switch from engineering to something else, like it's not like you have harder classes to do because you already did a bunch of hard classes. So pretty much like you just fit that in other stuff. So I mean, there's really no way to upgrade from that unless you're doing neuroscience, maybe. Sorry, Arib. Okay. Kwang, tell us about yourself. I know you already. Are you here even?
Yeah, but
You're
you
so
know I cannot speak
responsible.
English well, right?
Oh,
My name is Quang, and this is my final year at ECC, and I will transfer to UIC this year,
okay.
this semester. And I major in computer science, and I want to be a game developer.
Oh,
Because I already a game developer right now, but I just want to enhance my major.
okay.
Yeah,
Cool.
I also take 18 credit this year, and hope that, like Burfin saying, let's hope that that's going well.
Well, good luck with those 18 credits. You guys are making me nervous. All right. Thanks, Kwang. Eli, you're next.
Well, hello. Yeah, I'm a student actually over at NIU.
Mhm.
My major is geology, and hopefully I'll be graduating this semester, but we'll see. But I had gotten my associate's at ECC, so I figured I'd come back here for Calc 2 because I think you guys have a little bit better program as far as with the calculus and stuff like that. I wasn't too happy with Northern's.
Yeah, even online, as much as I hate for it to be online, I miss being in person. I do still feel like you get a little bit more personalized attention here. I was a GA at NIU, and I remember students coming into the math tutoring center at NIU and just kind of being like, I don't know, I'm in this lecture, and they're like, I don't know who, I barely even know the teacher, and it's just a totally different experience.
Yeah, it is. And actually, when I had taken Calc 1 through ECC and actually had you as a teacher, but it was during the summer and I worked construction, so I had to drop it because there was no way I could get the homework done. So once I saw you were the teacher, I was like, all right, good, because I liked your teaching style before. So hopefully I could stick in this class.
When was that?
It was like 2 years ago.
Whoa, crazy. Because usually I recognize names, and yours didn't pop up for me in my.
I was only in the class for like a week, and then I dropped.
Oh, okay. Gotcha. All right, well, cool. Glad to have you back. All right, let's see. The next person on my list, is it Supna? Am I saying it right? I think. Looking person. You know what? I do not see this person. Okay. Jenny. Jenny is next.
Hi, well, my name is Jenny, and I'm currently 17. I'm a dual credit student, and I also attend Elgin High School. And I plan on majoring in biomedical engineering, and, fingers crossed, like after I get my Associates of Science at ECC and then graduate from Elgin High School, hopefully I'll get accepted into Northwestern University. That's like my #1 school right now. Well, fingers crossed, because it's really hard to get in, but yeah.
Yeah, my sister got accepted at Northwestern. This was like 15 years ago, and she didn't expect she was going to get in, so she enrolled elsewhere, and she was like, holy cow, they let me in, but I can't afford it. And then they gave her a full scholarship, and she was like, okay, guess I'm going to Northwestern. But yeah, it's, if you can get in, that'd be awesome. Yeah, cool. I already feel like I kind of know you because I've been emailing back and forth with you for like 2 weeks now. All right, well, I'm glad that you are here. Greg, I know you. Wait, are you talking? Because I can't hear you.
Oh, okay.
There you go.
Yeah. I'm Greg. I did this over the summer. It's a bit rushed. I hope it's going to be a bit slower now and a bit more paced. We did integrals in like what, 3 weeks or something. So, I'm hoping that we can just kind of, ease through things, because I know this is going to be a bit more. Anything else? I don't think so.
So my notes for you are that you hope this semester goes slow.
Well, compared to summer.
Yeah, of course. Yeah, you'll have a little more time to digest the material. The difference being in summer, you probably only had like maybe 2 classes, whereas in the fall you have like 4 or 5. So maybe. What do you plan to major in, Greg?
Either computer science or business. I know NIU has a program with both, and I'm planning on investigating that kind of when I get to that point. But I'm still around that area, and I know that calculus it's pretty important for a lot of computer science area stuff.
Yeah. Anytime a student is like, I don't know if I'm going to need Calc 2, I might need it, I'm always just like, take it, get it out of the way. You might need it, and you don't want to wait. Just do it. Okay, good. Joe, do I have 1 Joe this semester or 2? I have 1 Joe.
Hi, yep, I'm Joe. This is going to be my last semester at ECC. I'm going to go into NIU in the spring. I'm looking to go for a chemistry degree and then work in the pharmaceutical industry in some capacity.
Okay. That sounds like a great plan. Cool. You guys, some of you are just so efficient at answering all my questions, unless you have anything to add to it. Deep, is Deep here?
Yep.
All right. I'm sorry. I'm only smiling because I swear I used to date this guy named Deepan Patel.
Yeah, right.
And I was like, Deep. Okay.
Okay, so I'm Deep Patel. I'm from India, and I came here 8 years ago at US, and at UCC, it's my second year. It's probably next year I'm going to transfer to UIC, and I'm also majoring at computer science.
Okay.
That's
Cool.
it.
All right. Awesome. Thank you. Let's see who's next on here. Jared.
Hi, I'm Jared. I'm my second year now of being at ECC. Been going for my major in environmental engineering. I'm going to be transferring after my associates to U of I because they have a nice engineering program down there.
Yeah.
And I'm going to be, I do know that a lot of chemistry and calculus is used in a lot of the engineering fields, especially in the environmental fields, because you got to know how everything connects together with all that. So it's going to be a very important class for me. So I'm very
Definitely,
excited
yeah.
for it.
Oh, good. Good. Yeah. Environmental, I think, is a really great field to get into. Seems like there would be a ton of job opportunities. I could be wrong, but I don't see how you could go wrong with that. Okay, good. I'm glad you're excited. Malik?
Can you guys hear me?
Yep.
All right. Hey, everyone. My name is Malik. Actually took your class last semester, and I recognize a bunch of names in the class.
Yeah.
So welcome back, everybody. We're back together.
Isn't it nice? Because some of the people who had their cameras on before, now you're like,
Yes.
wait, I recognize them versus
Yes.
just recognizing their name.
Yep.
See?
Indeed. It's really good. So my major is computer science. This is my final year at ECC, and I plan to transfer to UIC for software engineering with a concentration in that. Yeah, that's basically all I have.
Okay.
And also, I definitely agree with Greg on the point where everything felt really rushed in the 2 months that we had
8 weeks.
and learning of it. So yeah, hopefully it's a little bit easier pace than it was during the summer.
Yeah. Yeah. I hope so. Better be. We have twice the time, so.
Yes.
Okay. All right, good. Mariano, I also know you. Where are you? Mariano, there he is.
Hey, yes. So my name's Mariano. This is my second year here. I had you last semester for Calc 1 and I failed it. So I had to retake it in the summer and I passed it. So I'm good now.
Oh, good. Who did you have in the summer? Sorry, I'm totally nosy now.
I forgot her name, but
So
I think
she
her first
really
name
had
was-
an impact on you then.
her first name was Kathy, I think. I don't remember.
Oh, was it Mushan?
I think so, yeah.
I had her for Calc 3 when I was a student at ECC a long time ago. She's like old school for me.
Yeah, she is. And I plan to major in computer engineering and hopefully to go to University of Iowa. Yeah, that's
Oh,
about it.
why Iowa?
Because my cousin goes there and I got some friends that go there too. So it seems
I
pretty
think they have like a transfer agreement with Illinois, don't they?
I think so, yeah.
The tuition. And yeah, the courses transfer there nicely, I think. Okay, good. All right, Luca. Luca, there's Luca. I don't hear anything, but I see your name. Won't let me unmute myself. Okay. Are you just trying to get off the hook here, Luca? What's happening? Can you just type in what you're majoring in so that we know? I'm always curious. And I'll see if I've got only 2 more after you. All right, you work on that, Luca. Alberto, I know you. Where are you?
Hello.
Hello. All right, tell us about yourself.
Well, I took your class last summer. Oh, Luca's talking.
Oh, okay. I'll get to Luca right after you finish.
Oh,
Go
all
ahead.
right. All right. Yeah, I took your class during summertime for Calc 1.
Mm-hmm. And it was awesome.
It was pretty good. I liked it. I like the way you teach.
Okay, good.
All right. This is my last semester at ECC, actually. I already got my associates in science last semester, but I
Oh,
was
you
too
did?
late. Yeah, but I was too late to apply for NIU.
Oh.
So, whatever. So yeah, I'm majoring in geology. So
Okay.
yeah.
You are majoring in geology, and Eli is almost done at NIU in geology. Crazy. So are you starting there then in the spring?
Yeah, that's my plan now.
Okay. All right. Well, that's a good plan. I wasn't thinking that this was fall semester. I don't know. All semesters are just running together for me now. So when you said it was your last semester, it just didn't even occur to me like you'll be switching out mid-year. It happens. It's not like a weird thing to do. It just didn't occur to me. Okay, Luca says, yes, he's a part-time dual credit student. He goes to Larkin High School, doesn't know what he wants to major in yet. All right. Gotcha. I think we have 3 high school students. We always have the high school students these days, and they're so good. Okay, awesome. So I'm glad to have you here, Luca. Last but not least, okay. I said your name once properly last semester, and then I avoided saying it ever again because I thought I was going to screw it up. So I'm going to say it phonetically this time and write it down. Yenshin?
Oh, yes. I know a lot of people have difficult to pronounce my name. It is Yanxian.
Yenshin.
Yes. And actually, at the beginning, I'm not register your class, but at the first day, and I took another teacher's class, and I decided to change 2 of my other courses just to register your class. So I really like your way of teaching. Before I took the calculus 1, everyone told me calculus 1 is difficult, but after taking your class in the summer, I think it's pretty funny, pretty interesting. I think the math is fun.
Good. Well, you did well. So, and Calc 2 is, I think, harder than Calc 1, but some people don't think so. It's really random. But I'm glad you rearranged your schedule. I think some of the other classes do lots of things like discussion boards and like a lot of like video guides and things like that. And I have to tell you, I hated doing discussion boards as a student. I always felt like it was just busy work and it wasn't really contributing to anything I was doing. And I was just thinking about like, oh, I'm supposed to write 3 comments. What am I going to write? And the last thing I want to do is make you guys spend time doing discussion boards. If you want, I think I can start a blank one that if you feel like talking to each other on it on D2L, you can, but I'm certainly not going to require any sort of discussion board. Just, I don't really personally feel like it's going to be that useful. Now, I don't know if you talked to anybody who had my Calc 2 class in the spring, but I had picked up an asynchronous class. Wait, did someone raise their hand? Because something beeped at me, but I don't see the hand raise. And I don't see a comment.
Zane did.
Oh, Zane. Oh, now I see it. Oh, what's up?
Yeah, I took Calc 1 at UIC, and it was just so terrible. There was like pretty much just like you said, like a lot of discussion. It was so unorganized. So that's why actually I'm taking it here. I'm hoping for a much better experience. I can already see that reflecting here. So I'm looking forward to it.
Thank you. I mean, I just am trying to make this as much like a traditional class as I can. And I know that's hard to do, especially with the way I ended up having to do one day asynchronous. It's kind of a long story, but I will not get into it. I really wanted to do both nights synchronous, and like I said, long story, it did not work out. So unfortunately, you're gonna have like, you know, the same amount of time that we're here tonight in asynchronous work. So I just want to also make sure that what was it? You know, I was on a train of thought before that. So I want to make sure we know asynchronous work. I want to make sure everyone understands what's coming up. When I picked up a Calc 2 class last spring, it was another instructor's and they were getting rid of it. It was fully asynchronous, and I was thinking like, well, she already has the whole shell built up, so I'm just going to use this, but it did not work for me at all. So if you had heard anything about like what had happened in that class, it's going to be more, if you took my Calc 1 class, that's what this class is pretty much going to be like. I'm not going to be doing video guides. I'm not going to be doing discussion boards or group projects or like, no, that was just like a nightmare. It did not work for me. So I really just want to make this as much like a regular class as I possibly can. Unfortunately, with the asynchronous time though, like you're going to have the discipline to make sure that you're actually watching the asynchronous video each week. So, and instead of making a bunch of little small videos, I'm going to have it as like a lecture. So if you want to kind of set in your mind, like, okay, maybe on like Friday night, I'm going to sit down and act like I'm in class and watch this lecture. Just cut out some time to make sure that you do that each week, because you'd be surprised how quickly Wednesday will roll around again. And then you'll be like, oh my gosh, I missed the whole asynchronous lecture. And now I'm behind, because half this class is going to take place asynchronously. Now, that being said, I mentioned this in the video that I put out for you already, but I will after tonight, and I'm probably going to do this tonight just while I'm still on this train of thought. I'm going to pick up where I left off tonight and start recording another video for you. Now, in my mind, I'm kind of treating this like a Monday, Wednesday class, which was what I was originally going to have it as. So I'm treating this as though like I'm going to release this video to you probably by tomorrow morning, and you will have technically until Wednesday to watch it. But I wouldn't wait until Wednesday to watch it. Please make sure that you watch the asynchronous video by Monday at the latest. If you want, treat it like it's a Monday, Wednesday class, if that helps, unless you have something else going on Monday. But make sure that you do that. It's critical. I'm going to be talking about volume when I get into the asynchronous lecture that I'm going to be recording tonight and releasing to you probably tomorrow. So I will always release it to you by like Friday afternoon, probably Friday morning, because I'm not going to be recording anything during the day. I have children that I take care of, and that's not going to happen. But I want to make sure to give you time so that you can watch it at your leisure. Also, I understand though that once you get done with learning about area tonight, you're not going to be all of a sudden like, all right, well, let's watch another video like tomorrow, because you're going to need some time to process area and work on some homework problems and figure that out before you get into volume. So in some ways, it'll seem like things are moving quickly just because there's still just a lot of material to cover. When I wrote up the syllabus, I put out a tentative schedule. It's very tentative. I had mentioned in the video that test 1 is probably going to be the test that gets moved back. It might not, but the thing is, if I move a test, it has to go back a full week, because we're always going to be testing on Wednesdays, because I need to be able to proctor you. And then, what else was I going to say about the schedule? Oh yeah, there is definitely some wiggle room on the schedule where there are some of these topics, like every semester, end up just kind of being not as important, not necessarily optional, but if we don't have time for them, they're not going to really impact you later. And if something like that comes up, we can always get rid of it, or cut some things out of some sections. So if it looks like, holy cow, this is a lot, and maybe it doesn't look like it, but you'd be surprised what it can actually look like when you get into it. Especially some of those topics at the end of chapter 8 sometimes aren't really, if it's something you're never going to see again, it might be something that we can cut out, kind of depending on how we're feeling. And that's going to be a 10-section test too. Chapter 8 is one that I rarely get through all of. But some things like chapter 9, like that's going to be incredibly important to you heading into Calc 3. So we can't mess around with chapter 9. Stuff like that. So the schedule's tentative. That's my official plan if all goes perfectly, which it never really does, but we'll see how you guys do. It is a smaller class, which is kind of nice. It's only 18 students. So we'll see. All right. Well, I'm really glad that I had you guys go through and introduce yourselves. And I feel like hopefully it's helpful to you instead of just feeling like you're some passive observer in this class, that you can start to get an idea that there are actually other people in this class, other students doing the same thing that you are. You can contact each other. I think you have access to the class list on D2L, but if you are in other classes with other people, or if you're in a class with someone here and you're like, oh, hey, we're majoring in the same thing, or we're both going to the same school, do you want to meet up in the math lab? It's open. So if you're on campus, feel free to get together in groups. I know it's harder to form groups, and maybe you don't like studying in groups. I never did. I would always just talk. I never got any studying done. But if you work well with other people, please feel free to try to get into a group with somebody on here who you think you might work well with, if you would like. Okay. Without further ado, wait, are there any questions before I start talking about area? All right, then let us talk about area. I had gone over an integration review. I decided not to put up an assignment for it because I feel like you're going to be integrating so much that I'm not going to have you bother with it. But if you had any questions on that, you can let me know. Most of the integration that we're covering in this class, anything new or anything heavy, is going to be in chapter 7. The integration that you're going to see in chapter 6 is going to be pretty light. So mostly just, polynomials and power functions. I don't know if it's like the new version of the software I had to put on here, but I have to keep moving my camera physically. That's unfortunate. Okay, so 6.1, chapter 6 is all about applying integration. So all the integration techniques that you learned in chapter 5, and there weren't like a ton of them. I mean, you basically learned how to integrate power functions and simplifying functions to get them written as power functions, and some of the other things that I reviewed in the last video. But you're just going to be sort of putting that to work with applications that go along with that content. We're going to start out talking about area, and I really feel like talking about area, I mean, it comes before volume in the book, but it's essential to understand how to find the area between graphs before you start working on volume formulas, which we're going to be doing in 6.2, 6.3, and 6.4. So volume is going to be really like the big thing that we do in this chapter, and it takes up 3 sections. 2 of them are a little bigger, 6.2 and 6.3, and then in 6.4, it kind of shifts a little bit. But the volume is what we're going to spend the bulk of this chapter discussing, and then we're going to add on a little bit of arc length, surface area, and then we need to talk about work. And that's it. The rest of these topics are optional. We don't have to cover them. It's kind of like an if you have extra time thing, and no one ever has extra time. So if you want to look at 6.7 and 6.8, feel free to peruse those on your own, but they're not required for our class. But we'll start out with 6.1 here. if for some reason you can't see anything I'm writing, or if something's not clear, or my handwriting is not clear, please let me know. Pencil issues already. Okay, area between graphs. So when you were in Calc 1, you learned how to find the area under a curve, between the curve and the x-axis, and you were looking at the area under a curve from two endpoints A and B somewhere on the x-axis. This time, instead of talking about the area between a curve and the x-axis, we're going to focus on finding the area in between two curves. So I'm going to give you a definition here for how to do that. If f and g are continuous on the closed interval from A to B, and this is important, g of x is less than or equal to f of x, for all x in the closed interval, then the area of the region bounded by the graphs of f and g and the vertical lines x equals a and x equals b is the integral from A to B of f of x minus g of x dx. So f of x is the larger function in this case. G of x is the smaller function. You're going to be taking the larger function minus the smaller function. Now, I will give you an example at some point where your functions are going to intersect somewhere in the middle of that interval from A to B. And if that happens, you're going to have a situation where f and g are going to switch, because you're going to have one function that's larger and then a different function that's larger. If you're not used to thinking about functions in terms of inequalities, I mean, what the visual would be for something like this might be, let's say you have this function. I'm going to call it f. Let's call it f sub 1 of x. And then you might have another function that kind of comes through this way. And we'll call this f sub 2 of x. And, you know, this is just one possible example of a situation that could occur. So if you were trying to find the area between the curves, everything in this case regarding which function would be larger would depend on the x values at which you're cutting off that area. So if I was just looking at the area from A to maybe B sub 1, I'm going to call it B sub 1 because I have an idea brewing in my mind here for a B sub 2. Well, then you'd be looking at the area between the curves in between these two vertical lines. And in that case, your larger function would be, it's always going to be the top minus the bottom. So f sub 1 minus f sub 2 is how you'd be integrating this. However, if I instead decided to ask you for the area from A to B sub 2, well, you'd be looking at this entire area inside here. And at that point, you would need to figure out where these two curves intersected, because you would need to find the area from A to the intersection point. And in that case, f sub 1 would be the larger function. And then once you hit that intersection point, well, now it switches. And in this case, f sub 2 is the larger function. So it kind of depends on where you're chopping off your endpoints A and B for your closed interval. So we're going to be looking at situations where it's much more straightforward. You might even have a situation where, I don't know, let's say you have, this is f sub 1. I did too many curves. I mean, I could just ask you for the area, you know, from 0 to B sub 3. And in that case, you don't even have a curve on the bottom. You're just looking at the x-axis. So that would be a different situation. So it all just kind of depends on the situation that's occurring. So this would be more of like what you did in Calc 1 versus these two situations are Calc 2 situations. So I'm going to give you some examples. Does anyone have a question on the definition before I do that?
Wait, I have a question on like the example you just drew. So you said to decide whether like one of the functions is considered to be the larger function depends on where you put the endpoints, right?
Yeah.
And then you said something about the x values too, I think. I didn't catch that part.
The only reason the x values are going to even apply to us is just kind of where you're cutting off that area.
Okay.
It's the y values that we're really focusing on as far as which one are we subtracting from the other. Now, what you're going to see is if you accidentally switch f and g here, you're going to get the same exact answer for the area, except it's just going to be the negative version of it. So if you get a negative answer, you might want to check and make sure you didn't accidentally switch f and g. What I don't want you to do is if you get a negative answer, just like act like it didn't happen, erase the negative and circle it. If you got a negative answer, it could be that you switched the upper and the lower, or it could be that you did something wrong. So go check and just, you know, rewrite it because we want to be accurate here. Did I answer your question, Jenny? Okay, awesome. All right, so example 1. We're going to sort of build this up here. Find the area of the region bounded by f of x equals x cubed plus 3, g of x equals negative 2x minus 1, x equals 0, and x equals 1. Oh, I think it might finally rain. I did not do anything with my kids today because the whole day I was like, no, it's about to rain. It's about to rain. And it never did. Such is life. It's probably for the best. It was just gross outside. Okay, now, personally, if I can graph these by hand, I graph them by hand. You don't have to have graph paper, but you're going to need to know which function's top and which one's bottom. You, of course, can put this into your graphing calculator. You might decide that since you're in an online course and your computer is pretty much always in front of you, you might get used to using Desmos graphing all the time. So if you go to desmos.com and you click on graphing calculator, you can graph these on the calculator and look right at them. So I don't want to spend like a whole time doing a graphing tutorial. I'm going to jot down what the graphs of these functions look like. Negative 2x minus 1 has a slope of negative 2 and a y-intercept of negative 1. So kind of going to go like this. But you can graph these in your graphing calculator or on Desmos, whichever you prefer. The reason I like to graph these by hand is because if I do have to find an intersection point, assuming that I did a good job graphing these by hand, I won't have to actually do any algebra to find the intersection point. I'll be able to see like, okay, this point is on this graph and this point is on this graph. That won't happen in this instance, but it could happen in the future, and it will very soon. So negative 2x minus 1 is right here. Your cubic function is being shifted up 3 units. I also think it's good for us to remember how these graphs work. It normally has a turning point at 0, 0. We'll bump that up to 0, 3. And then it's got points at going up 1 and down 1. And then you go up to 2, 8 and negative 2, negative 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh, but I'm up 3. 1, 2, 3, 4, 5. So your cubic function has a point at negative 2, negative 5, and you can always make a table of values also if you want to do it that way. 2 cubed is 8 plus 3 is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And in this case, it's not even going to really matter exactly. You just want to get a good idea of what these graphs are doing so that you can see which one's the top function and which one's the bottom function. So this one is y equals x cubed plus 3. I was going to ask, does anyone want to see this on Desmos? But you know what? Since it's new to some of you, I'm going to just show it real quick. Stop presenting here. VES, MOS. I'm going to share in a sec here. All right, DESMOS.com. And I had mentioned in the video that you already watched that there's a link to this in Achieve, but it's very easy to get to. So whether you want to use that link or not, it's basically gets you to the exact same place. So you'll have x cubed, use the caret to get the cube, plus 3, and I guess you don't even need y equals, crazy. And then you have negative 2x minus 1. You can see how that works. If you choose to do it that way, you might want to, I mean, if you're working on it, just kind of jot down what you're seeing. Personally, I like to have it in front of me. That's up to you. Any questions on Desmos before I move back to my paper? Oh, you know what? I think on Desmos, I also said that these were bounded by x equals 0. I don't know if you can do this. You can. X equals 1. You can do so many things because it'll do non-functions. You can probably even play around with it and get it to shade, although you really don't need to. So the area that we're looking at is going to be the area between 0 and 1, and it's bounded by these two graphs. So you're looking at the area that's underneath this cubic function between 0 and 1, and then all the way down, not just to the x-axis, which is what you would have done in Calc 1, but all the way down until you hit negative 2x minus 1. So like I said, I think you can mess around with the settings and get this to shade. I'm sure you can, but I'm not going to do that right now. If you want to, it's something we can explore in the office hour. I think I've done it before. I just don't remember how. But anyway, this is the area we're looking at. So from top to bottom. And now that you're thinking about this in terms of top to bottom, because we're thinking about which function's larger, notice that these two aren't going to switch from 0 to 1. Like, let's say I was looking at the area from negative 2 to 0. Well, in that case, I have a larger function being this linear one, and the smaller function's the cubic. And then as I move my way over here, I see that they intersect at some point, and then I would have a switch between the top function and the bottom function. But I don't need to worry about that because I'm only looking at the area between 0 and 1. And in that area, it's very important to understand that the larger function is always going to be this cubic function, and the smaller function is always going to be the linear function. So we are going to set up our integral now. So in this case, I told you we're looking at the area between 0 and 1. If you want to shade it, that's fine. You don't have to. I'm not going to force you to graph these. I just think it's helpful for you as you work through these to graph them. Not going to make you do it. Okay. So this is the area that I'm looking for right here. So I'm going to set up my integral. I'm going from a to b. I'm taking the top function minus the bottom function. So the a to b is wherever I'm going from x to x. So in this case, I'm going from x equals 0 to x equals 1, which I listed for you in the problem statement. And then I'm going to take the top function, which is x cubed plus 3. I'm using parentheses in this case. You don't always need them. In this one, you do. So I tend to use them regardless. Top function minus the bottom function. And like I said, when we work on volume, this is going to be even more important that we are able to visualize what's happening with these graphs. So I'm going top to bottom, and I'm subtracting off the function that's on the bottom, which is negative 2x minus 1. And here's where, even though you might set up the integral correctly, you want to make sure that you actually simplify this properly using algebra. For instance, you want to make sure that this negative sign gets distributed. If you forget your parentheses, it might not get distributed. That's why it's really important to put those parentheses on there anytime you have more than one term that you're subtracting off. Before I proceed, questions here? Okay, remember, if you have a question, you can hit the raise hand and I'll hear it beep, and then I'll figure out who asked me the question. Otherwise, I'm not going to keep asking, although I want to make sure that I'm inviting you to ask questions if you do have them, but don't be shy. This is not supposed to be just one-sided. Okay, so I'm going to simplify this as much as I can, which in this case just means that I'm going to distribute that negative sign and then add the constants together. So minus negative 2x is plus 2x. And then I have 3 minus negative 1, which is 3 plus 1, which is 4. And another, issue with parentheses here, you don't technically have to have them, but anytime you have more than one term inside your integral, you should have it offset with parentheses. So you can see that's your entire integrand. And now you're just going to integrate. We did questions just like this in the integration review. I think I might not have even done anything this basic. It's just a polynomial function. So I'm going to go ahead and increase the exponent by 1 and divide by the new exponent. Increase the exponent by 1, divide by the new exponent. If there is no variable on it, you're just going to add a variable. The integral of a constant is just that constant times x. And then this quantity is going to get evaluated from 0 to 1 using the fundamental theorem of calculus. And this is driving me crazy written in this form, so I'm going to simplify it before I apply the FTC. So I have 1/4 x to the 4th power plus x squared plus 4x. We're going to take that from 0 to 1. And I'm going to evaluate this entire expression at 1, and then we're going to subtract off this entire expression evaluated at 0. So we have 1/4 times 1 to the 4th plus 1 squared plus 4 times 1. Now, I realize that I have got students in this class with vastly different comfort levels with algebra and arithmetic. Some of you will be writing all of this down, and others will be kind of skipping a few steps here and there on the arithmetic. Just make sure that you're showing enough work that it makes sense. Like, for instance, I don't want you skipping down from here to here even. Like, at least show me your integral before you integrated. And I don't want you skipping from here. Well, actually, that would make sense. But I don't want you skipping from here to here. Actually, show me the integral and then evaluate it. So I understand some things that you would skip. You don't have to write out every little thing. I write more than I expect to see from you, just because I'm always anticipating that a student's going to ask a question. So I try to preempt that by just writing extra stuff. Okay, now if it's a polynomial and you're evaluating it at 0, it's going to zero out on those terms. You don't have to show this if you know that you're going to plug in 0 and all those terms are going to go to 0. I'm showing it this time. I might not show it later. Just be careful, because that won't always be the case, and students tend to just think that, oh, well, one of my limits of integration is 0, therefore I don't need to evaluate it. And that's not true. It depends completely on the function. That's only true in this case because we have a polynomial. So I have 1/4 plus 1 plus 4, which is 5 plus 1/4. 5 plus 1/4 is 21/4. If you're wondering if you should leave this as a decimal or a fraction, this is technically it's a terminating decimal. So if you did write this as 5.25, fine, that's fine. If it was something like 5 2/3, I would want you to give me the improper fraction. That being said, yeah, don't leave this as 5 1/4 as a mixed number. We don't usually use mixed numbers in calculus. Write it as an improper fraction. And only give me a decimal if it terminates, not if it's a repeating decimal. I don't want to see any rounding. Okay, questions on this one? All right, your first example in Calc 2 is done and dusted. Now we move on to example 2. Students tend to find section 6.1 to be pretty accessible. It's the volume that starts to throw people a little bit, but area usually isn't too problematic. Stephen, what is your question?
I should have just asked immediately, but could you just leave it as like 5 plus 1/4? Because like I'm kind of used to like leaving it in like that form, I guess, like to where you've simplified it like enough, but like not like over crazy simplifying it, I guess.
Oh no, simplify it all the way. Yeah.
Okay.
Yeah,
Okay.
all the way. Get me an actual answer in
Okay.
one term. Yeah, I'm glad you asked. Anyone else? All right, let us see here. Example 2. Oh. Find the area of the region bounded by, sorry, that actually says region. My handwriting gets a little funky as I move to the right because I run into my document camera and there's nowhere for my hand to go. Maybe we can adjust. All right, find the area of the region bounded by f of x equals x squared plus 8x plus 13, and g of x equals negative x minus 1. Now this time I didn't actually give you any sort of vertical boundaries. So you're going to have to graph this to figure that out. Okay. Now, only because this topic is going to come up in chapter 7, am I going to do this right now. You can also do this in Desmos, but I'm going to graph this parabola and I'm going to do it by hand by completing the square. And like I said, I would not be doing this if this topic wasn't going to come up again in chapter 7, but I kind of feel like it's a good idea to plant these seeds right now and remind you of completing the square. And then when we talk about it again later, hopefully it will be already kind of a work in progress. You did learn how to do this in college algebra or algebra 2, but you might not remember is what I'm thinking. So you learned how to graph quadratic functions. Now, technically you can graph this just by plotting points. I'm gonna, though, put it into vertex form. When you did this in college algebra, you did something called completing the square. And when you did that, you took the constant and you brought it over to the other side. And then you asked yourself, what number do I need to add to both sides to make this a perfect square trinomial? So you took half of the middle terms or half of the linear terms coefficient and you squared it and you added it to both sides. So you're going to take 1/2 of 8, which is 4. And then 4 squared is 16. So 16 is the number that you're going to add to both sides. Remember, it's an equation, so what you do to one side, you must do to both sides. Now, the whole point of that was so that now I can write the right-hand side as a binomial squared because it is a perfect square trinomial. So I can rewrite this now as y minus 3 equals x plus 4 squared. If you don't remember how to factor perfect square trinomials, you take the variable to the first power, or you cut the power in half, depending, it could be a higher power of x. And then you take that number that was half of the linear terms coefficient, and you add that in. The plus sign is there because you had a plus sign, and then you square the quantity. The nice thing is you can always check it to verify that it's still the same. If you were to FOIL this out, you would indeed get x squared plus 8x plus 16. And if you're wondering why the heck are we doing this, well, now you will see, oh, whoops. Yeah, put my square in the wrong spot. That you have an equation written in vertex form. If you don't remember vertex form, the vertex form was y equals, technically it was a times x minus h squared plus k. Jared, what's your question?
I think you might have misadded your numbers for the 13 and the 16. You put negative or minus 3 instead of plus 3.
Oh, I did. Thank you. Thank you. Isn't that wild? Little tiny things. Someone's got to tell me when something like that happens. My vertex would have been in the wrong spot. Yes. Negative 13 plus 16 is indeed positive 3. And then when you subtract it from both sides, we end up getting negative 3 on the right, or minus 3. All right, so here's your vertex form. This gives you a vertex of HK. If you'll remember, you always take the opposite of this value, or you just think about it as taking the value that follows the minus sign. So the vertex is HK, and that means that the vertex of our parabola is going to be negative 4, negative 3. Now, we're not going to be graphing parabolas in chapter 7, but we are going to be using completing the square to get integrals into specific forms, which is, like I said, why we're going to be using this later. Burfin, yes.
How'd you get -4 again?
Oh, so that's a good question. Let me rewrite this actually. Technically, we could say this is y equals x minus -4. Sorry if that's super small. Because we can rewrite the plus as minus a negative, and h is whatever follows the minus sign. So the value that follows the minus sign is -4.
So you basically like formed it into the vertex form, right? Like to make it look negative?
Yes, yeah, to make it look like it was a subtraction. And some students always just think about this as taking the opposite. So they're thinking like, okay, if this is +4, then I'll switch it over to minus, but that only works for h, not for k. Trying to think what else you did that for. Arib, what's your question?
Yeah, so we can get -4 this way, but can we also get if we just do opposite b over 2a, or is that something else?
Oh, yeah, you can do that too. To find the vertex, yes,
Okay.
-b over 2a and f of -b over 2a. Yeah, so there was a formula for that. The reason I did it this way is because completing the square was a concept for chapter 7, but absolutely you can find the vertex by taking -b over 2a and f of -b over 2a. So if all you were going to do was graph this, you could do that also. Where of course a is 1, b is 8, and c is, we wouldn't need c, but c would be 13.
Okay, thank you.
You're welcome. Other questions here? Wonderful. All right, so I'm going to graph this parabola. Now, notice also my vertex form has an A in front of it. In our situation, A is 1, which is why this works out nicely for us. A basically dictates how wide or narrow the parabola is going to open. With A being 1, it's a standard parabola. So we're just taking y equals x squared, and we're shifting it. We're shifting it which direction, 4 units? Oh, I already gave you the vertex, so I guess it doesn't really count to ask you that question. It's going to go left 4 units and then down 3 units. You can also see that by looking at this equation. That's what I was thinking when Burfin asked me that question. When you guys were doing transformations, anytime you had something in parentheses and you were thinking about shifting it horizontally, left or right, it was like the opposite. So if you have x plus 4, it moves to the left 4. But that doesn't count if it's outside the parentheses. So -3 means you're moving down. I mean, it's all from college algebra or algebra 2 whenever you saw that. So it might be like in the cobwebs of your mind. But you kind of talked about this concept when you were shifting your graphs around. So this is just going to be the graph of y equals x squared shifted left 4, down 3, because the vertex is at -4, -3. I'm going to graph this now, and then we'll do the calculus on it. 1, 2, 3, 4, 1, 2, 3. Okay, so there's your vertex. You don't even need to fill in the points if you know what your standard parabola y equals x squared does. Remember, it goes up 1 to the left and to the right. If you want to label these points, even you can. I'm just going to label my vertex. And then remember with y equals x squared, so if x is 1, y is 1, but if x is 2, y is 4. So when I go 2 to the right, I'm going to go up 4, and this one I'll label for you. This one is going to be at -2, 1. Sometimes it's hard to know where to label. Do the best you can. And then I'm going to also go 2, 4 the other direction. So that's going to be right here. And this is going to be at 1, 2, 3, 4, 5, 6, -6, +1. So we can now piece these 5 points together to draw our parabola. Because I think we're going to use it, I'm even going to put one more point on here. So if x equals 3, 3 squared is 9. So you can go over 3 and then 9. So you're going up 5 more units. 1, 2, 3, 4, 5. And then you're going through here. And then let me figure out what this point is and we'll label it. So we were at -4, we added 9. So we're at -7, positive. I'm only trying to illustrate here that you'll have less work to do if you make a nice graph. So there's your parabola. Nothing new has actually been done at this point. It's all algebra. Your other equation that has been so long forgotten about is -x minus 1. So let's graph that. The y-intercept is at -1. The slope is -1, so it's going to go down 1, right 1, down 1, right 1. But we don't really care about what happens over here. All we care about is what's happening between these graphs. So 1 point will get me up to here at -1, 0. And look what happens. I have an intersection. That's good. Now, if you continue to follow this slope, left 1, up 1, left 1, up 1, you will be able to get to your other point. I might not have made my ticks well enough. Let's see if I did. I think I did. So this will be your parabola. Okay, so my whole point in doing this was that you can see if you do a nice job graphing it, you won't have to do any algebra to actually find the intersection points, but you're going to have to show me that. So if you don't actually solve for the intersection points, you need to give me a very good graph where I can very clearly see they're right there, you've got them. But I will show you how to do this algebraically, because if you don't give me a good graph and you can't find them, you're going to, and sometimes you're not going to be able to find nice integer ones. You're only going to be able to find crazy ones. We've got this situation. I will show you how to also do this algebraically. Okay, but this is officially what your graph looks like. We're trying to find the area of the region bounded by this graph, -x minus 1, and your parabola. Now notice, and you're going to want to check this, verify that throughout the entire region, your top function doesn't change. That's key here. No matter what I do, starting from the leftist endpoint of my region, all the way till I get to the rightmost endpoint of my region, I'm never going to have a situation where this linear graph is not the top graph. This is always going to be the top one. And then my parabola is always going to be below that. All of the points on this parabola, once I get past the leftmost intersection and up to the rightmost intersection, are going to be below the linear ones. So now if you can see this, you can go ahead and set up your integral, and you're going to take it from x equals -7, because that's the leftmost x value that you're looking at in this region, to x equals -2, which is the rightmost x value in your region. But I'm going to show you how to solve for the intersection algebraically, which is, again, an algebra topic. Solve for the intersection. Because you're going to need to know where to cut this off. I asked you for the area between the graphs, nothing more. And this is the only area that's going to be between those graphs. Once you move to the right or to the left of the intersections, they're never going to cross again. So what you're going to do is you're going to set the graphs equal to each other. You officially have y equals x squared plus 8x plus 13 and y equals -x minus 1. You can solve this system of equations by just setting them equal to each other. You want to know, when does this graph equal this graph. Now, if you don't remember how to solve quadratic equations, remember that all of the terms need to be on one side and you need to have 0 on the other side. So we're going to get x squared plus 8x plus x plus 13 plus 1 equals 0. And then you'll simplify and solve. Now, you can always use the quadratic formula anytime in your life. It's always there for you. However, if you can solve it by factoring, that would be the easiest thing to do. So you'd be looking for two numbers that multiply to 14 and add to 9. And those two numbers are indeed positive 7 and positive 2. So now you have x equals negative 2 and x equals negative 7 as your intersection points. So however you find those, just make sure that I can clearly see that you've done some work to find them. Then you can set up your integral. Before I set this up, are there any questions about the intersections or the graph? So let's set this up. We're going to go from left to right. So even though it might seem like it's counterintuitive to start at negative 7 because that's the higher absolute value, negative 7 is less than negative 2. So you're going to take the area from negative 7 to negative 2 of the top function minus the bottom function. So your top function is negative x minus 1. And then subtract off the bottom function. Use parentheses, x squared plus 8x plus 13. Don't forget your dx. My Calc 2 teacher would take off points if we didn't put our dx's on our integrals. All right, now you're going to simplify and integrate. So we are at negative x squared. You have negative x minus 8x, which is negative 9x, and negative 1 minus 13, which is negative 14 dx. And if this looks familiar, it's because you saw something very similar to this when you solve for your intersection, when you set these equal to each other. If you want to factor out the negative and leave it outside of the integral, you can. I'm just going to leave it in. We'll have negative 1/3 x cubed minus 9/2 x squared minus 14x. And we're going to evaluate that expression first at the upper limit of integration, negative 2, and we'll subtract off the evaluation at negative 7. Be really careful here because there are a lot of negative signs going on, like a lot of them. It almost makes me want to factor that negative out, but I think we'll be okay. Up to you. So we'll have negative 1/3 times negative 2 cubed minus 9/2 times negative 2 squared minus 14 times negative 2. And then we're going to take off the evaluation at the lower endpoint. So you have negative 1/3 times negative 7 cubed minus 9/2 times negative 7 squared minus 14 times negative 7. And if you want to put this all in your calculator, that's totally fine. If you don't trust yourself, simplify it a little bit first. I'm going to just pop this in my calculator and give it to you in smaller pieces. So minus 9/2 times negative 2 squared minus 14 times It's -2. Oh, you know, at a certain point in the evening, this stops working properly. That's okay. You guys know how to use your calculators. All right, so for the first one, I am getting 38 thirds. And then we'll do the same thing at -7. And I'm getting -49/6. Moment of truth. Did I enter this into my calculator properly? 38 thirds plus 49/6 is 125/6. Which is indeed the value that you should obtain. If you have questions about how to enter some of these expressions in your calculator, that would also be a really great topic for the office hour. But if you have general questions, let me know right now. I gotta turn on a light. I cannot see anything. Okay, so there's a little bit more going on with that one because of the intersection points. Some of them will be really super straightforward, where you might have like 2 linears and then maybe like a vertical line. This one is one of those where you're going to have to solve for those intersections. I have a trig one planned for you next. Okay, before I do the trig one, any questions on this one that are lingering? You know what's great about you guys having your cameras on? It helps so much because instead of me being like, are there any questions? And then people replying back, nope, we're good. Because like, that's not that helpful. If I can see you just being like, no, like it's just this visual where I'm like, okay, we're all on the same page. It's really helpful. So I really appreciate that. Why didn't we divide the -14 by x like the rest of the numbers? Here? Well, when we're integrating it, because it's a constant, it doesn't have a variable on it. So we have to put the variable on it. And anytime you're integrating a constant, so like let's say your constant is k, the integral of k is just going to be kx. And if you think about this in terms of derivatives, working your way backwards, the derivative of 14x is 14. There you would lop off the variable. So yeah, so we wouldn't move it into the denominator because if you think about 14 as being like 14x to the 0, because remember if x to the 0 is just 1, you can think about this as increasing the power by 1 and dividing by the new exponent, and you'll get 14x. That's kind of why that works. But anytime you're integrating a constant, you just plop your variable onto it. Does that answer your question? Okay, excellent. Don't want to lose track of my notes. All right, so this one is example 3. Find the area of the region bounded by f of x equals the sine of 2x. Don't freak out. G of x equals the cosine of x. And I'm going to give you some bounds for x, and then we're going to discuss how to use them. X is going to go from negative pi over 2 to pi over 6. Now, trig for some of you guys was a year ago. For others, it was like 10 years ago, maybe more. I'm going to jot these down real quick. These functions are pretty straightforward to graph. And then we'll talk about how to use these bounds. So the cosine of x, remember, starts at 1, and then at the end of its period, it ends up back at 1, and then it goes down to -1 in the middle. It has x-intercepts at pi over 2 and 3 pi over 2. And since we have our x going to negative values, we might want to run this the other direction also. Unfortunately, I'm only going to get mine halfway there because I didn't leave myself enough space. What a bummer. Okay, so that's my x-intercept. It's my low point. Okay, so this will be negative pi over 2 because we are going to be discussing that. And then our cosine function goes, kind of curves. Oh man, I wanted it to be curvier than that. Okay. Going through and then back up, so on and so forth. And then it's going to do the same thing on the other side. Like that. So this is y equals the cosine of x. Now for the sine of 2x, remember that the period of your function was 2 pi over b for sine and cosine. And b was the constant multiple on your variable inside the function. So remember, if the 2 had been in front of the function, that would affect the amplitude. It would go up to 2 instead of going up to 1, and down to -2 instead of down to -1. But in this case, because it's inside your function, that affects the period of the function. So it's 2 pi over 2, which is pi. So this graph is going to complete its period in half of its normal time. So the sine function starts at 0, 0. And normally it will go up at pi over 2 as an x-intercept at pi. It'll go down and back up again. This time it's going to complete its whole run in pi. So it's going to have to go all the way up to 1 in the middle here. And it's going to have its x-intercept here at pi over 2. At 3 pi over 4, it's going to hit its low value, and then it's going to head back up again. Trying to make this as accurate as possible with my hand sketch. So it's going to sort of do something like this. And we don't care what happens beyond that because we're only looking at values between negative pi over 2 and pi over 6. But I do want to talk about what happens as it moves to the left. This is negative pi. So we're going to go, once again, down to our lowest point at negative pi over 4, up to our x-intercept at negative pi over 2. The highest point in the amplitude is at negative 3 pi over 4, and then it goes back down again. Something like that. No, I should have done these in different colors. What was I thinking? But this is y equals sine 2x. Okay, but you can kind of see here what looks like is happening is when we're talking about this region from negative pi over 2 to pi over 6, we're going definitely from here and definitely going all the way up to 0. But what happens over here on the right is a little bit sketchy because there's a little bit of a switch here that happens between the two functions. Right here, the cosine function, I'm going to mark it just so that we can very clearly see it. This is the cosine function. This is your sine function. It looks like it starts out where the cosine function's on top, and then they intersect. And once you get further out, the sine function's the top function. So what we're going to do is we're going to look for the intersection point. Now, it might be the case that the intersection point is at pi over 6, in which case we don't need to worry about it anymore. We can just set up our integral. But if it's not, we're going to have to set up another integral and switch the upper and lower functions. So to solve for these, for this intersection point, I'm going to get a little practice with this. Once again, we're going to set these two graphs equal to each other, or the two functions, I should say. Sine 2x equals cosine x. You probably have not solved the trig equation in a long time, and that's okay. I put some trig identities in the content section of D2L. So there's a whole trig sheet on there with a bunch of identities. Basically, having a 2x and an x together in the same equation is really not ideal. We want to switch this out. So if I were you, I would use the identity for the double angle for sine and rewrite this as 2 sine x cosine x. That's probably what you did in trig to solve these equations. And then you probably thought like, oh, I'm never going to use this again, which is unfortunate. Let's get everything on the same side because we're going to get this to factor. So we have 2 sine x cos x minus cos x equals 0. And now you can factor a cosine x out of each term, and that leaves you with 2 sine x minus 1 equals 0. And hopefully this is ringing some bells. If it's not, put a big highlighted box around it and make a note to yourself to look at it later. I don't know. Unfortunately, with trig equations, there are so many different types that it's really hard to study all of them over again in Calc 2. Okay, cosine x equals 0. So we'll use the 0 factor property here and set each factor equal to 0. And then you'll have to know what these values are. So the cosine of x is 0 at pi over 2, negative pi over 2. And honestly, you can look at the graph to, you know, the graph will have your x-intercepts on it that'll tell you where the graph is equal to 0. So right there, right there. But remember, when you're looking at where the cosine of x is equal to 0, you're thinking about the unit circle and you're looking at the x value on the unit circle. So the x value on your unit circle is going to be 0 at your upper and lower poles, which is pi over 2, negative pi over 2. So that's kind of where that comes from. Now for this one, well, you're looking at where does sine x equal a half. This one you can also look at that unit circle for on your trig sheet. I mean, technically you should know this because it's a special angle and it's from trig, but I realize that it has been a while. So definitely if you need to check this in your calculator or something, be my guest. Some of you will think about this as being 30 degrees and then you'll convert it to radians. You'll say, okay, well, I know it's pi over 6, and then bingo, you don't need to go any farther because now you know that pi over 6 is an intersection point. And if you know that these two intersect at pi over 6, well, we can say that we're looking at the area from negative pi over 2 to, and then this intersection, I'm going to try to mark it as well as I can, is pi over 6. So we actually lucked out here and we don't have a situation where the top and bottom functions switch. Most of the time you'll find that this will pan out nicely for you. Not always, but most of the time. Sorry, I should zoom out a little bit. It makes everything smaller, but like there's a lot to look at here. All right, so there's your graph. We verified that we have intersections at -π/2 and at π/6. So now we can go ahead and say that, well, if these two graphs intersect at π/6, then it must be the case that all the way up to that intersection point, the top function is always going to be cosine. And I don't need to worry about those two functions switching. Now, let's say I had asked you to find the area from -π/2 to π/2. Well, then you'd have a different situation, because in this little region right here, you would have to switch the upper and lower functions and you'd have to add that area on. So if that's something you want to look at in the office hour, we can totally do that. But it would be just a second integral that would go from π/6 in that case up to π/2, and you would just be switching your subtraction. Because in that case, your top function would be sine 2x and your bottom would be cosine x. Okay, I'm going to set up this integral. I feel like a lot just happened. Does anybody have a question? So we are looking for the area from -π/2 to π/6, and I'm going to take the top function minus the bottom function. So cosine x minus sine 2x. dx. All right, so now you just have to remember how to integrate sine and cosine functions. If you had Calc 1 with me, then you probably learned to just kind of do these backwards, thinking about their derivatives. But I know that the derivative of sine is cosine, so it must be the fact that the integral of cosine is positive sine. The thing that people screw up most with this is just the sign, S-I-G-N, on their integral. Okay, now I know that the derivative of cosine is negative sine. So whatever goes here is actually going to be positive, because I know that to get from positive sine to negative, or I'm sorry, from cosine to sine, the cosine is going to be positive. Its derivative, sine, is going to be negative. So I already have that. Now, if you want, you can do a u substitution. You don't have to, because in this situation, gosh, you know what? Your book didn't actually give you a formula for this like the old book did. I think is it on the sheet? I'm going to see. But basically, when you're looking at sine kx or cosine kx, the integral is just going to be 1 over k and then times your normal integral. I'm going to see if that's on your sheet. Here. Sorry, I have like 55 tabs open here and I don't know why. Yes, Deep, go ahead.
Okay, so like, how did you get plus sine x plus 1/2 times cosine 2x?
I worked my way backwards, but you don't even have to do that. You can just say, okay, well, I'm going to look at the formula sheet and the integral of sine is negative cosine. So the integral of negative sine is positive cosine.
Oh, okay, okay. Got it, got
You can
it.
do it that way too.
Gotcha.
I am glad you asked. Like I said, the thing that gets messed up the most with these trig integrals is just the SIGN sign that goes on each term. You would be shocked how many wrong answers pop out of that. I'm looking at your formula sheet right now. Derivatives and integrals. This one might not be on here. I mean, they basically just list it as a u substitution. If you wanted to do it as a u substitution, you would just let u be 2x. Du is 2dx, and you don't have 2dx, you just have dx. So you would divide out the 2. It was the last book that I did that had that 1/k formula in it. Go ahead, Jenny.
Wait, so you got the 1/2 cosine 2x by taking, like, using the formula you said? There was, like, a formula for it?
Yeah, let me write it down for you. It was, you know, they keep changing the book on me, and I keep forgetting what book I'm in, and it was the Rogoski book that we used to have like a year ago that actually gave a formula for it. So it was the integral of cosine kx dx is 1/k sine kx plus c. And then the integral of sine kx dx equals negative 1/k cosine kx plus c. You don't have to use those. If you took Calc 1 using the Sullivan book, then you never learned these. So I think they're helpful in Calc 2 just because you do these integrals a lot, and I think you'll do them enough that you won't even think about this. You're just gonna divide out the constant multiple. But that's what the formulas look like. So
Okay, thank you.
is cosine. You're welcome. And the derivative of cosine is negative sine, hence where that negative comes in. So you may feel free to highlight those and use them at your leisure. I'll highlight mine. All right. So now that we've integrated, now we just have to actually evaluate the function. So we have the sine of pi/6 plus 1/2 times the cosine of 2pi/6, which is pi/3, minus the sine of negative pi/2 plus 1/2 the cosine of negative pi. So negative pi/2 times 2 being negative pi. So the sine of pi/6 is 1/2. The cosine of pi/3 is 1/2. Then we have minus. Don't forget to distribute your negative sign or just use some more parentheses. The sine of negative pi/2 is -1. And the cosine of negative pi is -1. You got to know your trig values here. Plus 1 plus 1/2. It's 2 1/4, which is 9/4. I want to give you an example now where we switch our variable of integration. Before I do that, does anyone have a question on example 3? Example 4. Find the area bounded by. All right, I'm going to give you these equations written in terms of y. X equals y squared minus 5 and x equals negative 2y minus 2. Now, technically, you can set up any sort of area situation using an x equation or a y equation. This one is specifically given to you written as x equals because this one it suits itself to being done this way. And I'm going to show you what I mean. If you are like me and you have a really hard time thinking about this in terms of x because you're so used to or in terms of being written as an equation x equals, because you're so used to always seeing y equals, just for graphing purposes, you might want to rewrite these as y equals so you can get a good idea of what's happening with the graphs. With Desmos, at least, you can just type them in as x equals, and that sort of changes the game. When you go back to in-person learning, eventually, some of you will probably be done with college before that ever happens. You won't have Desmos sitting there at your side when you take a test. And I guess that's kind of why I've always based my instruction off of that idea that you only have your TI at your disposal. Either way, this one we would write as y squared equals x plus 5. And if we were trying to graph this and write this as y equals, if you were trying to get y by itself, we could take the square root of both sides. When we do that, we need to apply a plus or minus. Because I can always take the negative square root, square it, and still get y squared. Now the other one is a little bit easier to work with just because all we have to do is solve for y. So you have x plus 2 is negative 2y. And then y equals, and then divide every term by negative 2. So you'll have negative 1/2 x and then minus 1. And that's just because I said y equals x divided by negative 2 plus 2 divided by negative 2. That's where that came from. So we have 2 different equations here that we can graph. Now they're written in terms of functions, and then I'll show you why you want to think about these in terms of y and not x. Okay. So let's see. The square root. You learned how to graph square roots. This one is being shifted left 5 units. Because it's happening on the inside of the function. And when it's happening inside the function, we do the opposite of what the sign is telling us to do. So again, this is something that you could technically graph on your graphing calculator, but you're taking your radical function and shifting it left 5 units. So 1, 2, 3, 4, 5, and that's where its vertex will be. And your radical function goes up by 1, and then it goes over by 4 and up by 2. If you haven't graphed these in a while. You can always use a table of values also. If x is negative 1, negative 1 plus 5 is 4. The square root of 4 is 2. That's kind of why that does what it does. But it's going to do the same thing underneath because this is a plus or minus. So whatever it does on the top, we can reflect on the bottom. Kind of like that. If you want to take this out further, you might want to do that. I know that if, for instance, if I go over 9 units, I'll go up 3 because I know that the square root of 9 is 3. So 1, 2, 3, 4, 3. And I can do the same on the bottom now. 4 and -3. And then you can draw this nice sideways parabola. If you didn't recognize this just by looking at the form of the equation, you might not have seen these in a very long time. I don't even remember when you're taught these. I think it is college algebra, but you don't see them in this form. But it looks like this. It's just a parabola on its side. It's not a function because it doesn't pass the vertical line test, but that's what it looks like. So we're going to write this as x equals y squared minus 5. Some students are really good at just like shifting their paper 90 degrees and just graphing this in terms of y, or I'm sorry, in terms of x. I don't know. I just rewrite it. That's just me. Your other function is -1/2 x minus 1. So -1/2 means you're going down 1, right 2. So you're going to end up here and then down 1, right 2. If you've done a really good job graphing this, you'll see that this is going to be the intersection point. And I'm going to guess that this point right here is going to be your other intersection point. So you'll go up 1, left 2, and up 1, left 2. And you do indeed get these 2 intersections if you graph these so nicely. And I'm going to connect them. So this is x equals -2y minus 2. Okay, now I want to show you that this can technically be done by integrating with respect to x. So if you wanted to set up a dx integral, you could. However, the problem is that your top function is not consistent throughout this region. We're looking at the region bounded by these 2 graphs. That means anything that's in between their intersection points. So that is this area here. Now, if you look at this closely, you'll see that from -5 up to -4, the top function is actually y equals the square root of x plus 5, and the bottom function is y equals negative square root of x plus 5. You know what? I'll label it here to make it clearer. So this is going to be a switch. Your bottom function all the time is going to be y equals negative square root x plus 5, but your top function is going to change. So once you hit this boundary line at x equals -4, the top function switches. It's no longer the quadratic function, but it becomes y equals -1/2 x minus 1. So you absolutely can do this with respect to x. It's just going to be harder. The function you're going to be dealing with is going to be harder because it's a radical function and it's not a polynomial. This is a polynomial. It's very easy to integrate. Once you switch your integral over to a radical, it becomes harder to integrate. Sometimes it will require skills you don't even have at this point, like chapter 7 skills. So sometimes you won't be able to do these problems if you don't actually do it the easier way, if you set up your integral wrong or in the most complicated way possible that wasn't intended. So what you're going to do here is you're going to switch this over to a dy integral. When you use a dy integral, you're no longer thinking top minus bottom because that's what we're trying to avoid here. Instead of going top minus bottom and integrating from left to right, you're going to do the opposite. You're going to go for the integral from, let's call it c to d. So this will be bottom to top. instead of left to right. And then your functions are going to be f of y minus g of y dy, where f of y is going to be your function on the right. And g of y is going to be your function on the left. So it's going to work very similarly. I think it just is a little bit harder for students to see right minus left versus top minus bottom. There's something about top minus bottom that's clearer to us. I don't know what it is. I think also because we read, most of us read anyway, from left to right for reading in English. If you're looking from right to left, it's sort of counterintuitive. But that is the way that we're going to do this when we set up these integrals. We're going to go right minus left, and then we'll integrate from the y value, lowest point of the intersection, up to the y value, the highest point of the intersection. And everything's going to be written here in terms of y. Yes, Jenny, go ahead.
So when we use like the dy integral, is it specifically like for like when we do these type of problems where like we're given things in terms of like x, or did I miss you saying something about when we specifically use the dy integral?
So sometimes it's going to be a dead giveaway because the problem statement is going to be written as x equals instead of y equals. So if the problem statement is written like that, then you are definitely going to be using a dy integral. But there are going to be other cases where the problem statement is not written that way, and you're going to do the graph and you're going to look at it and be like, this sure would be a lot easier if I used a dy integral. You have the opportunity to use whichever you would like. So it's kind of up to you to learn how to recognize which one's going to be easier and which one to use. And when I write your exam for this chapter, I'm going to give you some area problems, and I mean, I might specifically give you something like this, but even if I don't, if I write everything in terms of y and you switch it over to x equals, fine. I've had students do that before, where they completely change the solution process from what I was expecting them to do, but they still get the right answer. So it's kind of whatever works best for you, but definitely if it's presented like this, I would definitely know that it's wanting you to use a dy integral. Does that answer your question?
Yes, thank you.
Okay. All right, so let's go ahead and set up our dy integral. So we're going to take the area and we're going to go from the lowest y value up to the highest in the region. So the lowest y value that you're seeing here is actually at this intersection point, which is -3. The highest one is going to be at the top intersection point. Don't think about this one because this is not the highest value in the region. You're going all the way up to the highest value in your region, and this is occurring at 1. And by the way, I didn't do this, which I should have, but this intersection can be solved for the same way that we did this previously. To find the y values for the intersection, you're going to take your original equations that I gave you and set them equal to each other. So like I said, if you do a great job graphing it and I can clearly see the intersections, then you don't actually have to show me this. But some students will do this even just to check their work. So you can solve this quadratic equation and you will get these same two values of y to pop out. So y -1, y +3, and you'll get y equals -3 and y equals +1. And your visual here is you're just kind of sweeping the area. So think about the shaded part. This is kind of why I like to have this on my paper. I'm just sweeping over the region from right to left. So I'm looking at what is the rightmost value that's covered and how far down does it go. So I'm looking right here at this intersection. It goes down to -3. and I sweep over it. And as I scan it, I'm scanning for how high does it go. And how high it goes in our case is 1. And you're going this way. So you're kind of thinking like, all right, I'm moving through the region as I had from right to left. And that takes some getting used to. And make sure that whatever you do, you're not entering -5 to +4 as your limits of integration. Your limits of integration on a dy integral go from bottom to top, not from right to left. That switches. That's the difference with the dy. So when you set up your integral, you're taking the right function, which is -2y minus 2, minus the left function, which is your quadratic function, y squared minus 5 dy. And then you'll simplify that and integrate. Before I do that, does anyone have a question on the setup? So we're going to go from -3 to 1. I like to go in descending order, but you absolutely don't have to. -y squared minus 2y. I have -2 plus 5, which is +3. And you'll see this behavior as you work your way through, where you have this opposite situation. And then you'll integrate and evaluate using the FTC. So -1/3 y cubed minus 2 divided by 2 is 1. So just y squared plus 3y. And we'll take that from -3 to 1. And then I'm going to subtract off -1/3 times -3 cubed minus -3 squared plus 3 times -3. And again, you don't have to write out every little piece, but if something goes wrong, I'll be able to at least give you partial credit if you write this all out versus putting it all on your calculator from here and just giving me a wrong answer. Then how can I give you any partial credit? I didn't see your work. And when you pop this into your calculator, you should get 32/3. You're going to notice that a lot of these answers, the type of fraction that you're going to get pops up a lot. Lots of thirds and sixths. And most of these will not simplify to nice values. Okay, so I have 1 minute. If you would like to stick around for the office hour, I will be on for 20 more minutes after this. I had gotten a question from one of you about why the calendar meeting time was set to 8:10. And that's just because you guys are entitled to a 10-minute break in this class. So I generally just let students out 10 minutes early versus cutting the class off in the middle and then sending everybody away to do what they want to do and come back. I always feel like that takes more time than 10 minutes by the time everybody comes back and gets back to the thought we were on. I'm just going to stop at 8:10, but I will be on my office hour until 8:30. So if you have questions, stick around. If you'd like to see an extension of anything that we did in this, like a lot of students would be like, what if this had happened? Or what if you had that? And that's a great thing to talk about in the office hour. And I'm supposed to call them student hours because it's not time for me to just do clerical work. I will do that if you don't have questions. But even if you're just like, I think I might have a question, but I'm not sure, that's fine. I'll be here in the background and you can just pop in when you do have a question. I'm going to put up it should be actually available to you now on Achieve, the 6.1 homework. I had it set to release at, I don't know, like 8:10 or something, 8 o'clock, something like that. So it should be available to you now. Let me know if you have any issues with it. I forgot to check into if there's like an Ask My Instructor button for it. I don't remember seeing one. Gosh, I don't know. If I go to student preview, I don't know if there's an Ask My Instructor button. What will I do with all my time if I don't have all these instructor questions? There is not. Yikes. Okay. So, oh man, I'm actually doing a review of Achieve for Pearson right now, and this is wow. This is gonna be like, wow. No, Ask My Instructor. Yeah, I don't see it in my preview. I didn't know if maybe my preview is missing it. It's not on the resources. Screenshots, you guys, you're gonna have to email me and screenshot. Make use of the office hour, make use of the tutoring center. I will be on the office hour Monday from 5 to 6 o'clock, but I am gonna be releasing more information for you regarding volume, probably tomorrow morning. So there's a lot of math coming your way. So keep up with it. If you have questions in the meantime, email me. Like I said, I will be on till 8:30, so I don't want to keep you. I'm already keeping you 2 minutes too long, and now I feel bad. But do stay on if you have questions. Otherwise, have a wonderful evening, and I won't see you till Wednesday. But watch the video that I'm going to post tomorrow.
All right, I hope you have a great night.
You too. Thank you. I don't know if I should record the office hour.
You usually don't. At least you didn't last semester.
I know sometimes I regretted it, and then other times it was left recording, and then I regretted that. Because I was like, wow, we were talking about stuff that I didn't really want recorded.
I do have a question.